Okay, so let us start today's discussion by addressing this issue that we had about what we did in the last video. So you know what I am talking about. We have two non-zero rings A and B, and F is a homomorphism from A to B. If Q is a prime ideal of this ring B, then F inverse of Q is a prime ideal of A. If you remember the proof, I would say proof of course because this is a claim. We did something like this in that proof. Okay, we used the correspondence theorem for rings to have this isomorphism. And then, as the authors suggest, this is a subring of B slash Q, this quotient ring. Actually, the authors did not say anything about this ring. They simply said that this quotient ring is isomorphic to some subring of this. Now, in my attempt to do things quickly and in a sleek manner, I have actually made a mistake. Initially, I thought that it's just a minor thing, and if I make some small change, it can be rectified. But unfortunately, that's not the case. The problem is with this part. It will be more clear if I draw a diagram. Say this is your ring A and this is your ring B. It's not given that F is onto. F is just a homomorphism. And as such, the image of A under F may not be the entire ring B. So the problem is that the ideal Q in B may not be a subset of F of A. It may be like this. In that case, this symbol becomes meaningless. Okay, because in this case, if this is the case, if a portion of Q lies outside of F of A, then Q is not an ideal of F of A. It's not even a subset. So how can I form this quotient? It does not make sense. And my use of the correspondence theorem itself also has been wrong, because the correspondence theorem requires F to be onto. In fact, at the time of writing this itself, I sensed that I did something wrong, but I wasn't really able to see what. In a desperate attempt to have an onto function, I did consider F of A, but forgot this part. Okay, so that was the mistake. That means this is how we cannot do it. We have to do it by some other means. So let's first complete this thing and then only we can move forward, because we cannot leave something unclear like this. Okay, so what can we now do? Now, in place of Q, what we will do is that we will consider the intersection of F of A and Q. That will definitely lie inside F of A, but will that be an ideal? So these questions are there. So let me write without writing sentences, let me just write the mathematical details. What I now claim is that this intersection, which is a subset of F of A, is actually an ideal of F of A. Oh, sorry. Not F inverse, but F of A intersection Q. This is an ideal of F of A and in fact is a prime ideal. Let's first see why. Well, one thing is immediately clear, that this is indeed a subset of F of A. Is it non-empty? Yes, it is non-empty. Why? Because you are taking the intersection of a subring of B and an ideal of B. we already know from properties of homomorphisms that f of A is a subring of B. So, being a subring, it has the 0 element of B. Being an ideal, Q also has the 0 element of B. So, at least 0 belongs to this intersection. It is not the empty set, it is non-empty. So, it is a non-empty subset of f of A. Fine. Is it a subgroup of f of A under addition? Yes. And that also is almost immediate. Why? Because f of A being a subring of B is a subgroup under addition. Subgroup of what? Subgroup of B. So, it is actually a group in itself under addition. Q being an ideal of B is also an additive subgroup of B. So, their intersection is automatically also an additive subgroup of B, okay, because intersections of subgroups are also subgroups. In particular, because this intersection lies inside this, so this is a subgroup of this as well under addition. Okay, so subgroup non-empty, okay, subgroup under addition, okay. Next, we have to prove that this is an ideal. So, for that, ideal in what ring? In this ring. So, we now need to consider an element in this intersection. How will that element look? See, that element needs to belong to f of A as well as Q. So, in general, it will look like this, f of A1, where A1 is some element of A and it also belongs to Q. Okay, so that's how we say we have chosen this element. And now we need to multiply this element by some element of f of A, which is going to look like from this side or that side, it doesn't matter because our rings are commutative. And that other element is going to look like this for some A2 coming from A. Now the question is this product again in this intersection? Well, one thing is immediately clear, that the product is also this, because f is a homomorphism and so respects multiplication. And that is why, because it looks like this, the product is in f of A. Is it in Q? Yes, it is in Q. Why? Because this f of A1 is after all an element of Q. Just forget about the fact that it looks like f of A1, it is just some element of Q. And f of A2 coming from here is after all coming from B, and Q is an ideal in B. So, this product also belongs to Q. So, it belongs to Q as well as f of A. So, it belongs to their intersection. That means this really is a legitimate ideal of f of A. The next thing to see is that this cannot be equal to f of A. That this is a proper ideal. How so? Well, if we forcefully suppose that this is equal to f of A, then f of A being a ring has an identity element 1 that needs to belong to this intersection, right? If then 1 has to belong to this intersection, and as such 1 has to belong to the ideal Q, but then Q has to be equal to B. Is that possible? No. Why? Because Q is a prime ideal and so by definition is a proper ideal. Q cannot be equal to B, and that is why this is not possible. This is actually a proper ideal of f of A. And finally, let us see how this is in fact a prime ideal of f of A. To see that, we need to take any two elements of f of A, take their product such that the product belongs to this ideal. then if we can prove that at least one of the elements belongs to the ideal, then it will be a prime ideal. So let us take two elements in A such that their product belongs to this. Well, then the product in particular belongs to Q as well, and Q is a prime ideal in B. And these elements, although they are coming from f of A, after all are inside B. So that is why either f of alpha 1 belongs to Q or f of alpha 2 belongs to Q. Now both of these elements, because of their structure, already belong to f of A. So if this is the case, then it belongs to the intersection, or if this is the case, then this belongs to the intersection. So we see that yes, this is in fact a prime ideal of f of A. Now we are going to use the correspondence theorem. Okay, so I kind of want to keep this part, so let me just erase this part. Correspondence theorem to what? To this slight modification of the homomorphism. We now replace B with the image of A under F. Now this is not simply a homomorphism but a surjective one. It is onto. And yes, now I can apply the correspondence theorem. And the correspondence theorem gives me an isomorphism like this, except now something will change. In place of the ideal Q, we are now going to consider this ideal of f of A. So by the correspondence theorem, A slash the F inverse, the inverse image of this will be isomorphic to f of A slash this. Now because this is, we just now proved that this is a prime ideal of f of A, so this is an integral domain, and that's why the isomorphic ring, this will also be an integral domain, which in turn implies that this is a prime ideal of A. But we did not want this, we wanted this. So did it all go in vain, so much work? No. Let's now look at this carefully. Recall the fact that inverse images behave well with almost anything, intersection, union, set inclusion. They just distribute themselves over everything. In particular, when you have intersection, it is this intersection F inverse of Q. Now, simple argument from function theory would tell you that this is equal to A. So you are getting this intersection. Now, you see, the domain of your function f is A, So any inverse image of any subset of B, whether that subset belongs to f of a or it intersects f of a or is disjoint with f of a, it does not matter. This inverse image by definition is a subset of A, and that is why very nicely actually we are getting f inverse of Q. So that's how this itself is a prime ideal of A. So this is the entire thing. Okay. So this issue has been completely answered, and now we can start our main thing for tonight. And that thing is the question of the supply of prime ideals in the type of rings that we are considering. We are considering commutative rings with identity element. Is it always the case? We have put so much importance on prime ideals. We have said that later on they are going to give us many things. Okay, so prime ideals are the focal point of commutative algebra. But if you say consider just any arbitrary ring, the type of ring we are considering, and you find out that there are no prime ideals, then that's a very bad situation. Luckily, that is never the case. Any ring that we consider which is commutative and has an identity element must have at least one maximal ideal, and we have already seen that maximal ideals are prime. So prime ideals are always there. That's the next thing, and it is 1, 3. Yeah. If A is a there is a condition, a very mild condition on the ring A, it has to be a non-zero ring. Then A has at least one maximal ideal. We are not going to prove it, and we will have to use Zorn's lemma from ordered theory of ordered sets. There is a section in the 8th chapter, I think, of Terence Tau's analysis, the last section, if I am remembering correctly, which deals with ordered sets, the different types of orders you can define on a set. I skipped that section entirely in the hope that viewers will do it themselves. I don't really know if that's the case, if anyone really saw that. Anyway, we are just going to see the basics of Zorn's lemma. I mean, at least the things that we need in order to understand Zorn's lemma. We won't prove it, however. You consider a set X, and you consider a binary relation on X, which means that it relates any two elements of X. So if two elements of X are given, say A and B, not necessarily distinct, either this relation relates A to B or it does not relate A to B. Okay, it's not necessary that any two elements are related, but it's a binary relation. Say it has these three properties. Number 1, reflexivity. You already know what reflexivity is. A should be related to A for all A in X. Number 2, antisymmetry. If A is less than or equal, I should not perhaps say less than or equal to, but A is related to B and B is related to A, where of course A and B are coming from X, then A has to be equal to B. That is antisymmetry. And the third one is transitivity. If A is related to B and B is related to C, then A is related to C. If this relation satisfies these three conditions, then it's called a partial order relation on X. A set X with a partial ordered relation on it, that is this pair, is called a partially ordered set, sometimes in short POSET, P-O-S-E-T. Zorn's lemma is about such sets. Now we need a few other things as well. Suppose you are in a partially ordered set like X with that partial ordered relation. Okay. Say you have a subset, let me call it Y. Okay, say Y is a subset of X. Alright. Now, an element B of X is said to be an upper bound of Y if Y is related to X for all Y belonging to Y. Oh, sorry, B. Yeah, sorry about that, B. Or you can write X also, whatever you want. So that's the notion of an upper bound, which is exactly like what you know from analysis. Upper bounds of sets of real numbers. Note that this B may or may not belong to Y. If it belongs to Y, then it will become the maximum element of Y. Maximum element, okay. So this is one thing. There is another thing. There is a reason this relation is called a partial order relation, because this type of relations do not necessarily relate any two elements. Do you get the point? You may encounter two elements in a partially ordered set, say X and Y, or say alpha and beta, which are not related. That is, for them, you do not have alpha less than or equal to beta, and you also do not have beta less than or equal to alpha. They are not comparable by the relation this. Such non-comparable elements may exist in a partial ordered relation, I mean in a partially ordered set. However, sometimes we encounter partially ordered sets in which that thing is true, that if you take any two elements, they are related to each other in one way or another, either like this or like this. And that's the case with the ordinary ordered relation that we have in the set of real numbers. If you take two real numbers A and B, either A is less than or equal to B or B is less than or equal to A. One of them has to happen, but that's not always the case. I'm not going more into these examples, okay. It just not is the case in general. However, if it is the case in a subset of X, say you encounter a subset T of X, then whatever properties this relation has on X obviously are also going to be true for the elements in T in particular. Additionally, T has this property that if you take any two elements A and B in T, then either A is less than or equal to B or B is less than or equal to A, means related to A. Both of them may be true also. In that case, they have to be equal. If you encounter such a state T, then T is called a totally ordered subset of X, or there is another name also. Such sets are called chains in X. Okay. We need one more thing about all these things. So you have seen what partially ordered sets are, what totally ordered sets or chains are. In a chain, any two elements are related in one way or another. But we still need one more thing. Again, assume that Y is a subset of X, where X is a partially ordered set. Suppose you encounter a special element. Let me call it, say, Z or Z. This element is an element of Y. Okay. What type of special element is it? You will not encounter or get another element in Y. There exists no element Y in Y which exceeds this element in this sense, such that this and such an element small y does not exist. Say that is the specialty of set, this element. In other words, it's like climbing a tree. You start climbing from the stem and then there are branches. Okay. If you follow a branch, at one point you have to stop. You get a leaf, right? Beyond the leaf, there is nothing. So it's like that, like a leaf. If so, then this is called a maximal element of Y. This Y may actually be equal to X. In that case, you get a maximal element in the entire partially ordered set. There is a difference between a maximum element and a maximal element. Maximum, if it exists, in this case, say B is an upper bound which belongs to Y, then B will be the maximum element of Y. That is unique. However, a maximal element is not unique. You may have more than one maximal element. And I don't want to drag it more than this. You probably already have seen these things here and there. So I just gathered them in one place. Now we can see the statement of Zorn's lemma. Okay, so here we go. Let this, do not have to write this all the time, every time, but simply I am writing, let this be a partially ordered set or coset such that, okay, we need non-emptiness also here. Be a non-empty poset in which every chain, every set like this has an upper bound. It's not necessary that all chains must have upper bound in just about every partially ordered set. That's not the case, but say it is the case here, in which every chain has an upper bound, then X has a maximal element. That is the Arm's lemma. It gives us the existence of at least one maximal element in every partially ordered set in which chains have upper bounds. And this lemma is used in many places. For example, you need this lemma to prove that every vector space has a basis. There are many situations like this where Zorn's lemma is used, and this is one such situation. Alright, so let us now come to our main proof. So the meaning of this is clear. Let me repeat once more. In a partially ordered set that is non-empty, if every chain has an upper bound, then the partially ordered set must have at least one maximal element, like that leaf where you reach and beyond that you cannot go. Proof. Okay, so A is a non-zero ring. We have to prove that A has at least one maximal ideal. Let, for some reason in the book the authors have used summation, means sigma, be the set of all proper ideals of A. Okay, so sigma is the collection of all proper ideals of A. Since the zero ideal belongs to sigma, sigma is non-empty. Why? Because A is itself a non-zero ring and zero ideal is always there. So zero ideal, because of this fact, is a proper ideal of A, and that's why it belongs to sigma. So sigma is non-empty. Now this is a partially ordered set, and that relation is set inclusion, our ordinary subset relation. It is a partial order on any collection of sets. It satisfies reflexivity. You can check it mentally. Every set is a subset of itself. It also satisfies antisymmetry. If A is a subset of B and B is a subset of A, then A and B are equal. And of course, transitivity. If A is a subset of B and B is a subset of C, then A is a subset of C. So it's a partial order. Okay, so we now are looking at a partially ordered set which is non-empty. Now to apply Zorn's lemma, we still have to prove that every chain has an upper bound. So let T be a chain in sigma. What this means is that T is a subset of sigma where any two elements are comparable. It's a totally ordered subset. It may be the empty set also. If then the zero ideal, that element in sigma, is an upper bound of t. I am not going to explain how this case is really a case, that is how the empty set is in fact a chain in any partially ordered set, and so this possibility can arise, and how 0 is an upper bound of t. I leave this, at least the explanation of this sentence to you entirely. Okay, you see why this is true. If you don't get it, please write in the comment section below. Now let us consider the other possibility, that t is non-empty. Now what we do not forget what we are dealing with. The elements in T are what? They are after all coming from sigma, so each one is a proper ideal of our ring A. So the elements in T are ideals. So we can consider their, what can I call it? Let me call it I. We can consider the union of the elements of T and say the elements are, the general element is J. Okay. Now the claim is that this I is actually a proper ideal of A. Usually unions never become ideal unless there is something special about the sets or the ideals whose union you are taking. And that special thing will come from the fact that T is a chain. Alright. Clearly, zero belongs to I. What is this 0? This 0 is the ordinary 0 element of our ring. Why does 0 belong to I? Well, because 0 is in every j here, and the non-emptiness of T ensures that we have at least one j in this union, so that the union itself is not empty, and that's why 0 belongs to I. So I now becomes, whatever it is a non-empty subset of A. Okay. Next, let us see how it's an ideal of A. Let us take two elements, say x and y in I. So each such element will belong to some j, not necessarily the same j, okay, because it's union. Then x belongs to j1 and y belongs to j2 for some j1 and j2 in T. And this is where the fact that T is a chain will play a role. Because T is a chain, these two elements are comparable to each other, either this way or that way. By what relation? By this relation. Since T is a chain, either J1 is contained in J2 or J2 is contained in J1. We assume, without loss of generality, that J2 is contained in J1. If so, then Y will also belong to J1. So, X and Y now belong to J1. But J1 is an ideal of A. Hence, the difference of X and Y, X minus Y, will belong to J1. and say ux also belongs to J1 for any u belonging to our ring, because J1 is an ideal. Thus, this belongs to I. That means if x minus y belongs to one set of the union, obviously it also belongs to the union, and similarly ux also belongs to I. Thus, I is an ideal of A. But we want to really show that a little more, that I is a proper ideal of A. If the identity element of the ring A belongs to I, then it will belong to some J Is that possible? No, because in that case J has to be equal to the whole ring. But what is the problem with that? See, the problem is that J is coming from T and T is a subset of sigma. So J also belongs to sigma, and the elements in sigma are proper ideals. None of them is equal to A. So that is why this is not possible. So 1 does not belong to I. So I, besides being an ideal of A, is actually a proper ideal of A. Hence, I belongs to sigma. Now note that I by definition is the union of all the elements of T. All the ideals which are elements of T, they unite and give us I. So obviously each one of them will be a subset of I that comes directly from what I is. Yeah, I can write J. For each J in T. So what does that tell us? It tells us that this element I in sigma is an upper bound for the chain T. Hence, upper bound of T in sigma. The upper bound has to belong to the partially ordered set. Okay, so that's why we, simply having I as an ideal is not enough. We want it to be a proper ideal. Now we can apply Zorn's lemma. So by Zorn's lemma, this partially ordered set has a maximal element. Let's call it M, say. Now what properties does M have? First of all, being an element of sigma, it is a proper ideal. M is a proper ideal of A. Is a proper ideal of A. But is M maximal? if let me show it here. Suppose m is not maximal, then you have another ideal n of A, which is a proper ideal of A and which properly contains m. Is that possible? Well, if n is an ideal of A of this type, if it is a proper ideal, then n obviously belongs to sigma. Alright. However, then you are getting an element n which goes beyond this leaf in this tree. I mean, I am not using technical word, just for understanding. In this tree, one branch has this leaf, beyond which there is nothing, above which. But if this is the case, then you do have something even above m. But that contradicts the maximality of m. That contradicts the fact that m is a maximal element of this partially ordered set. And that is why no such ideal n can exist. M is maximal as an ideal, and that's how we see that A must have at least one maximal ideal. So you do not have to worry about running out of maximal ideals and hence prime ideals. It has to, this result has to nice consequences, but I think the video has already become too long. So we will discuss this next week. And tomorrow we should have calculus, but because I have decided to start physics, so tomorrow we will start physics, class 11 physics. Let's start and see how far we can understand physics from scratch. Okay, and then once our mathematical preparation is sufficient, we will go to the advanced topics. So that's just it for tonight. See you tomorrow with elementary physics. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.